Let's look at Unit 11, Games in AI. In this unit, we'll look at how games are used in, how AI is used in games. We'll start by watching parts of the Sanford video for Unit 13. Unit 13 goes over a number of ways that AI is used in games. There's also another unit, Unit 14, after this, but that talks about game theory, which is more an area of economics and math, and so we won't be reviewing that unit. We'll be skipping that one. So in this one, Stanford walks you through the basic questions about AI in games and how it can be used, and talks about the difference between a single-player game and a two-player game where you have an opponent, and introduces this idea of a min-max tree, a tree search where you are trying to maximize your score while your opponent is trying to minimize your score. It deals with time complexity. We look at chess and how chess has so many options that you just cannot explore them all. So, and then it goes in and talks about, oops, didn't mean to go there, how we can solve some of these problems with game theory and not search the entire tree, how to reduce where we are trying to search the tree. And also talks about the state space and how we can represent the state of a game with Pac-Man. So it's a nice unit that goes over the use of trees. But we're going to mainly focus on one part of it, and that is this min-max tree. This is a tree where, again, you are trying to maximize your points and your opponent is trying to minimize your points. And there's something called alpha-beta pruning, which where you can limit how much of the tree you have to explore. So I'm going to start by going over this example from Berkeley on the min-max tree with alpha-beta pruning. I'm going to run this Java app. There's a Java app at the bottom here. I'm going to get that running down here. Okay, but let's talk about generally how it works. Let's look at the game tic-tac-toe. So here we have a game tic-tac-toe, and here's it's X's turn, and that's us, and we're trying to maximize our score. So we have some different score. We have different options. We could go to these three different locations. So we could go here, and we get this board, or we could go here, and that gives us this board, or we could go here, and that would give us this board. So these are the three possible boards representing the three moves we can take. So for each of those boards, O has a number of options. O can go, like with this board, O can go here or here, and so there and there are the two options. Similar here, O can go two different options. And again, sometimes after that. And here we're going to score some boards. If we win, we're going to give this a +1. If no one wins, it's a 0. And if we lose, if O is win, we get a -1. And we're going to propagate this information up the tree using min-max. So at different levels, we're going to either do a max or a min. So at this level, we're going to do a max. At this level, we're going to do a min. At this level, we're going to do a max. So here, there's only one tree, and it's a +1, so we're going to maximize that and make this option a +1. Up here, at this level, we're going to minimize things, so we have a -1 and a +1, and we're going to minimize that and put up a -1 here. And here we got a -1, a -1, and a 0, and we're going to try to maximize that, and we're going to put up a 0 here. And what this will tell us is that the most likely scenario for this game. And so most likely we will choose this option because it's the maximum score. These two options we're likely to lose. So we're going to put our X here, which blocks O from winning right away. And then O is going to probably put an O here to block us from winning. And so that's because they're going to minimize their alternatives. So we talk about this min-max tree. We have to represent this tree. So here's an example of a tree with different options instead of game boards. And here's the numbers here. I'm just going to hit randomize to randomize these numbers. So again, this would be 7. This would be a good score for us. This would be a -6. This would be a bad score for us. And at this level, the algorithm minimizes the choices, and this one they maximize our choices. And so we can just start this algorithm and step through it. It goes down and visits these different values and compare. So it looks at all three of these, and it's going to minimize this and put the -2 up here. And then it's going to go over to this next algorithm, look at those values, and again minimize this and put a -3 up there, and minimize this. So now it's calculate all these values as minimum, and then it's going to maximize this value. So it's going to say this is a -2. So again, the most likely scenario, the best scenario for us is to go down here, because at this point our opponent is going to go here, and we're only going to lose by -2 here, where here we'd lose by -3, and here we'd lose by -6. You can actually set this up a little deeper and do what we call alpha beta pruning. And so then if you go through this, the computer is going to start, and at each point not just keep track of a min, but also keep track of a min and a max at each level. And there are some places where then the computer does not have to go on. For example, here it knew it was going to minimize these two values, and here we're going to maximize these values. So it found a 7 here, so it knew that this is going to be 7 or more, because again we select the maximum of these values. But up here we're going to select the minimum of these two, and 5 is already the minimum of 7, so it knows it's going to pick a 5 here, so it doesn't have to explore the whole tree. Now we're just losing one node here, but in general we could cut off whole sections of the tree. For example, if we're playing a game like chess or whatever, we can quickly see that this alternative path is much better than this path, because we could lose right away on this path, and so we can prune off that whole path. And so you can step through this, and it works to change the depth and change it to alpha beta pruning, and you can see how many points are pruned off. With a 4 deep tree you don't get that much pruning, but you should see 1 or 2 examples of pruning. Okay, so to get you a little practice for participation here, I've got a spreadsheet I want you to download. Yes, so the participation problem, we want you to download this spreadsheet, which is a similar tic-tac-toe game, but a little deeper and bigger. So here we have got a tic-tac-toe board, and X is going next, and so there are X go here, 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 here. So there's 5 possible options, and so this shows the 5 different places X could go. So these are the 5 options. So from here we can go to these 5 places. And from each of these, O could go to 4 places. So from here, O could go to 4 places. And so I've tried to color code that. So all those options are over here. O could go here, 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 or here. So this shows our board with O going to certain places. For this board, O could go here, 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 or here. Now then our tree is kind of getting kind of wide, so I made it go down here. So for this option, there are 3 places X could then go here, here, here. And so I've shown those down below here. So X could go here, here, or here. So these 3 go up to this one. These 3 go up to this one. These 3 go up to this one at this point. So all these go up here. And then, again, these 3 go up here. These 3 of the same color go up here, and you have to actually scroll over these 3 over here. Now in order for this to work with the leaf nodes down here, we need to score them. And if there's a winning value, it's easy to score them. So if there are 3 X's in a row, we can score that as +10. Saying that we won. So we're X in this case, and the opponent is O, so we won in that case. But if there are 3 O's in a row, then so up here O got 3 in a row and O won there. So we put that as a -10. But the other ones are a little harder to determine. Some of them look good, like here we have 2 X's in a row and then a blank, and so we're about to win there. So that should be a good board. And same here, we have 2 X's in a row and a blank. So there's a simple evaluation function we're going to use that I've tried to write up here. So again, 3 O's in a row is bad, we get a -10. 3 X's in a row is good, we get a +10. But if we don't have a winning or losing board, then we look for 2 X's and a blank anywhere. So any row, column, or diagonal that has 2 X's and blank, we get +4. And if we have two O's in a blank anywhere, we get a -4. Now also, if we get an O and a couple blanks, or an X and a couple blanks, we'll get +1 for the X, because we could still win there eventually. And in this case, we could still lose. So I want you to go through and evaluate this, especially start with these leaf nodes, which are the red boxes here, and evaluate this. So here we're looking down, this is, oh, and the last thing is anytime there's a mix of X and O's, it's not going to be any points. So I look at this column, there's a mix of X and O's. I look at this column, there's XX blank, so that's 4 points. And again, here's a mix of X and O's, that's nothing. Here, oops, we have a win here, so this is +10, so I can just put in a +10 here and stop evaluating as that goes. Now let's do one where we don't have a win. Here we've got an XX blank, so that's +4. Here's a mix of X and O's, nothing. Here's a mix of X and O's, nothing. So far we have +4. Let's do the columns. Mix of X and O, nothing. XX blank, that's +4. So now we're up to +8. Oh, but here we have a bad. This is a blank OO, so that's a -4. So we're at +8, and now we're at -4 more, so we're at +4. So we have 4, 4, and -4 means we're at 4. The last thing is we do have we have a diagonal here and here. This one has X's and O's in it mixed, so that doesn't count for anything. This one has a couple X's and a blank, so that's another 4 points. So I think this should score to a +8 as we go. And then again, we can score this one. Again, this one's relatively easy. We've got a win, so that's worth 10. Now, once you get these leaf nodes scored, you want to go up here, and what we'll do is this layer will maximize the scores below, and this layer will minimize, and this layer will maximize. So again, we've got a +10, an 8, and a +10. The maximum of that is +10 here. So we'll put in a +10 as we go here. And then eventually we will minimize these scores. So we'll look at these 4 scores here and put the minimum up here. Now, you can talk a little bit about alpha pruning here. We already have a -10 here, and since this is going to be minimized, we're going to put at least a -10 or worse up here. So this is going to be at least, since this is the minimum of these values, a -10 or more. So I want you to just go through, use this evaluation function if you can. Again, +4 for XX blank, -4 for OO blank, and if you have 2 blanks and an O, it's -1. 2 blanks and X is +1, and then again, -10 or +10 for a win or a lose. So update these red leaf nodes where needed, and then fill in these values here, and then with the maximum of the options below. And again, this will be the minimum of these options, and this would be the minimum of these options, and finally this should be the maximum of these options. So go through and fill out the min-max tree for this example. So that wraps it up for this unit. Hope you enjoyed learning how we can use min-max with AI in games.